This is another video for the lecture Intro PDE. We present section 2.2. This section contains a rough classification of second order PDEs and we will explain in this section the differential equations, which are the three differential equations which we will consider in the 3 chapters afterwards, so in the 3rd, 4th and 5th chapter. Okay, in the first chapter we only considered first order scalar PDEs and we found a more or less general method how to solve them. So now we consider scalar second order PDEs and we shall restrict to linear second order PDEs. Yeah, and then they have this general form here. Yeah, so we have a general coefficient of second order derivatives. Yeah, since the second order derivatives is given by 2 indices. Yeah, the coefficients is a matrix, n by n matrix. Then we have the first order derivatives, and then we have the function. Yeah, the first order derivatives, the coefficient is a vector, and for the function itself, the coefficient is just a function, a number. And we make the assumption that these coefficients may depend on x, but since it should be linear on u, yeah, we have this form. Okay, this is more or less the next more complicated PDE after we understood the first order scalar PDEs. Now, now we should say, and we will demonstrate this, there exists no general method to solve such second order linear PDEs. Even in this situation, yeah, we have different methods, and the behavior of the solutions and the whole theory, they strongly depend on the coefficients, and we will see they mainly depend on the highest order, on the coefficients of the highest derivatives. This means of the second derivatives. Okay, the simplest matrix is of course the unity matrix, and so the simplest example is B and C are 0 and A is the unique matrix. Then we have the Laplace operator. Since it's diagonal, we only have terms where j is equal to I, so we have squares of derivatives, and if all entries in the diagonal are 1, then this is just this Laplace operator. Okay, this is this is our first example in the 3rd chapter, and in the 3rd chapter we will derive many properties about the solutions and general method how to solve this equation. Yeah, the corresponding solutions which obey this equation are called harmonic functions. Yeah, and we will see that we can achieve in chapter 3 a very good understanding of these harmonic functions. Later, it turned out that all these properties and methods which we shall derive for the Laplace equation, yeah, can be generalized to more general situations, namely to the situation where the matrix AEJ is positive or negative definite. Yeah, so okay, now before we let us explain what this means. Also, first of all, since for any solution we assume that the solution is twice differentiable, then we know that the that this function here, that by Schwarz lemma, doesn't change. This expression, the second sum over the second derivatives, doesn't change if we replace the matrix A by the symmetric form of A. So we symmetrize A. Yeah, this form here is of course the symmetrized version of A, and this does not change. Yeah, since by Schwarz theorem, if we here reverse the indices or interchange the indices, we get the same expression since second derivatives commute. Okay, so both contribute by the same expression, so we get the same as before. And then later, when it turned out that the lower order derivatives can be controlled in terms of the higher order derivatives. Yeah, and this are done by so-called a priori estimates. And then this leads to the class of elliptic PDEs. So elliptic PDEs are first such linear equations where this matrix is either positive definite or negative definite. Of course, for all x, yeah, this has to be fulfilled for all x, and then one can see that then these methods which we develop only for in the third chapter only for the Laplace equation carries over. This class of elliptic PDEs is the most important class, and we offer another lecture, the lecture on PDE, which mainly introduces this elliptic theory. Okay, now this was a general observation over the time that there does not exist a general solution theory, but there exists classes of solutions which can be treated by similar methods. And so already so Jacobi was maybe the first who formulated in his lectures on dynamics the following general recipe. Yeah? The main obstacle for the integration of a given differential equation lies in the definition of adapted variables. Yeah? This means to find a method how to solve them, for which there is no general rule. For this reason, we should reverse the direction of our investigation and should endeavor to find for a successful substitution other problems which might be solved by the same method. Okay, so the strategy is to determine for any successful method all PDEs which can be solved by this method. Yeah, and this is what was really done after the one began to understand the Laplace equation. Yeah, one extended this. Yeah, we will see this. Yeah, there are very nice properties, and some of them are extended, and in this way we really the elliptic method, the elliptic theory was developed. Yeah, okay, so we introduced now second order elliptic PDEs, and later it turned out, yeah, after one already understood the linear elliptic PDEs quite good, one understood that this carries over also to non-linear elliptic PDEs. Yeah, and there is one example which played a major role in the development of the elliptic theory, and this is the minimal surface equation. And so the corresponding boundary value problems are called Plateau's problem. Yeah, so we have this equation, and we fix the value of u on the boundary of some domain. This is called then boundary value problem. And these equations describe, also the graphs of these equations are so-called minimal surfaces. These are surfaces that when you take an infinitesimal variation of the surface, so you perturb it locally a little bit, then in first order the total volume doesn't change. This is the defining property. Yeah, and typically the area is a minimum among all solutions. Among all surfaces which go through the fixed boundary. Yeah, and so this is Plateau's problem, and for the solution of this problem in the 1930s, Jesse Douglas received the first Fields Medal. Yeah, Fields Medal is the most important prize you can achieve as a mathematician, and this was we saw, and Jesse Douglas. So this is really a prominent problem, and was important for the development of the theory of elliptic PDEs, or more in general for PDEs. Now, so this is what I want to say for the elliptic class. Now there exists boundary cases. Yeah, there exists boundary cases, of course. Let's have a look again at our equation here. This is our linear equation, and the condition which we had for elliptic theory is that this matrix of the second derivatives is positive definite or negative definite. So all eigenvalues should be either positive or negative. So all eigenvalues should have the same sign. Yeah? We already understood that we can symmetrize. So after symmetrizing, this matrix is diagonalizable, and so clearly it defines, you should know from linear algebra that it defines a positive definite quadratic bilinear form if and only if all eigenvalues are positive, and vice versa for negative. Now, a limiting case is of course that A is semi-definite. So this means it has a non-trivial kernel, it has eigenvalue 0, but the eigenvalues which are non-zero have all the same sign. So this we call semi-definite. Okay, and this is of course a limiting cases. And the corresponding PDEs are called parabolic. So they are quite similar, and we will see for the most simplest example, the simplest example is just the heat equation, and we will generalize the method which we developed for the Laplace equation also to the heat equation. They have to be modified, but you will see that they are really similar. So these parabolic PDEs should be considered to belong to the boundary. So, and they form together with the elliptic PDEs an extended class of elliptic PDEs, which all share many properties. So in a general sense, these parabolic PDEs really belong to the elliptic class, and so the elliptic theory has always variants which apply for these limiting cases. So these are really similar. Now let's look at the simplest example, the heat equation, which we treat in chapter 4. Where comes the name from? The name comes from because this equation describes a diffusion process. So this means a process which levels inhomogeneities. And the name comes from from temperature. Yeah, that the function u describes the temperature, and then it describes a flow in direction of the gradient of the temperature, so of the steepest change of the gradient describes the direction of the steepest change, and so such diffusion processes, they describe a leveling of inhomogeneities. Yeah, this is a general feature of diffusion processes. And this, presumably you already know, or there's a deep relation between these heat equation and or general parabolic equations and stochastic processes. So also stochastic processes describe diffusion processes, and so there's a deep relation, and for this reason in the stochastic there's also a relation between the PDE theory of parabolic equations and the theory of stochastic processes. There also exists a nonlinear version which played a major role in the development of the theory, and this is the Ricci flow. Yeah, the Ricci flow. Richard Hamilton proposed in the 1970s a program that aims to prove the geometrization conjecture. Okay, what is this equation about? Here G is the Riemannian metric on a Riemannian manifold, and the right hand side is the Ricci curvature. Below I will define this, how they are defined, how the Ricci curvature is defined in terms of the Riemannian metric. Okay, and this Ricci flow, one can show that this is a diffusion-like process. So it also levels inhomogeneities of the metric. So the idea of Richard Hamilton was the following. He considered, what is the geometrization conjecture? The geometrization conjecture is a conjecture about free manifolds. So it tries to give a classification of free manifolds. Free manifolds are just subsets which looks locally like the Rn, like a vector space. So free manifolds are spaces which look locally like open subsets of R3. And an important conjecture, whose solution whose solution the AMS set a price of $1 million. This is the so-called Poincaré conjecture. It says that all simply connected free manifolds are, and the only simply connected free manifold is the sphere, the three-dimensional sphere. Okay, now let me explain the idea of Richard Hamilton. He put such a free manifold, then he put in an arbitrary Riemannian metric. This makes the free manifold to a metric space. It introduces just a metric in this space, but a metric which is compatible with this structure, so it's differentiable. And then he tried to control the long time behavior of this flow. And if he can control the limit in the long time behavior of this flow, then it's clear, since it's a diffusion process, in the limit the inhomogeneities should more or less disappear. And this is really what happens. in the limit, in the long time limit, if you can control the long time limit, then you always obtain free manifolds which have a large isometry group, a very large isometry group which acts transitively. So by isometries you can interchange any 2 points. Yeah, this means that the isometry group acts transitively. Yeah, so you have a really big isometries such that you can say more or less this manifold is homogeneous. Yeah, there are not anymore any inhomogeneities, and then it's reasonable and it's not so difficult that that one can then classify the homogeneous free manifolds. Yeah, and there exists a finite list. This was the starting point of the geometricization conjecture of Thurston. Yeah, and his conjecture states that one always can decompose any free manifold in pieces which have these symmetry groups, yeah, or which can be endowed with such Riemannian metric with such a large symmetry. Okay, this program, Richard Hamilton, yeah, was at some point couldn't finish the program. Yeah, there was mainly one obstacle. And a Russian mathematician, Grisha Perelman, maybe you noticed this because this was also in the media, that this Russian mathematician published in the internet 3 articles which overcome this last obstacle and lead to the first proof, yeah, of one of the millennium's problems. So this was a great success of geometric analysis. Okay, now this is all what I want to say to parabolic and elliptic PDEs, and now we come to the third class. The third class which we consider is that we have that this metric has signature. So it has eigenvalues of different signs, but in the hyperbolic situation we restrict to the situation that one eigenvalue has another sign than all other eigenvalues. Yeah, this is the situation of the wave equation. Yeah, here the simplest example is of course if it's diagonal, and then we obtain here the wave equation. Yeah, so here we have, like in the parabolic situation, the space variables, we have besides the usual space variables one t variable. Yeah, and of course this also counts as a variable of the function since it's part of the derivative with respect to t is part of the PDE. So we call this just time, t, because it represents time. And these equations, yeah, these have completely different behaviors and completely different solution methods. The solution methods of the wave equation, this is quite similar to the method of characteristic. Yeah, we again will have to find some trajectories. In this situation, it's exactly the trajectories of constant speed, of fixed constant speed, and then we can combine with, by the understanding of these trajectories, the solution. Yeah, and this wave equation we shall treat in chapter 5, in our last chapter. There was also an example for a system which was motivated, yeah, the investigation of this such wave equations and or in general of hyperbolic PDEs, and this is the theory of electrodynamics. So it's the Maxwell equations. Yeah? This is now a system of PDEs, and E and B. E is the electric field, B is the magnetic field, rho is the distribution of charge, and J describes the current. So this describes the flow of the charge, how the charge flows with respect to time. Yeah, and we have then such a concept. Yeah, the charge is a conserved quantity. So we have such a conservation law. So this means the total charge contained in an open subset can change only by the current which flows through the boundary of this subset, as we have seen before. Yeah, this is a simple consequence of this equation and the divergence theory. And there was also some nonlinear version, yeah, which was very important for the further development of the theory of hyperbolic PDEs. Yeah, I should say that hyperbolic PDEs are, besides this enlarged class of elliptic and parabolic PDEs, the second important class, and also quite good developed, have a quite good developed theory, but the theory is really completely different from elliptic theory. Yeah, this you will see by our considerations on the wave equations. Okay, and so there was also a nonlinear version, and these are Einstein's field equations of general relativity, yeah, which I also have written here. Okay, now, so we have this enlarged class of elliptic PDEs together with the parabolic at the boundary. Then we have the hyperbolic PDEs. So our classification of the linear second order PDEs distinguishes between elliptic PDEs, parabolic PDEs, and hyperbolic PDEs. And the two first we combine to a generalized class or enlarged class of elliptic theory. And the second one is the simplest and example of the hyperbolic class. Now I come to a third class, which is the main object of my research. This third class is a smaller class and less developed. I call this interglobal systems with Lax operator. So what means interglobal systems? Interglobal systems are nonlinear PDEs, or they can be also linear, which describe an evolution with respect to time, which is very stable. The term interglobal means it's very stable. So this means that the solutions have in a specific sense a maximal number of conserved quantities. Yeah, and this theory of interglobal systems is a part of the theory of Hamiltonian mechanics, which originated from Newton's description of the motion of planets and description of the gravity, how gravity between masses acts. Now, so inside this class of Hamilton mechanics, there exists special systems with a maximal number of conserved quantities, and they are called interglobal systems. Now, there was a new development. There was discovered in the 1970s and later a deep relation, which was completely unknown until that time, between interglobal systems and another field with a long history, so-called Riemann surfaces. Okay, and the discovery of this deep relation, this is quite interesting, yeah, because it starts with an observation of a Scottish lord who observed a wave, solitary wave, traveling along a channel, a Scottish channel. Yeah, and he got so excited that he wrote a report on waves. Yeah, he followed by horse the solitary waves over several miles, and then he got very excited and wrote a report on waves. And this report was quite influential. Yeah? Two Dutch mathematicians really translated his observation in a PDE describing the profile of a water wave which travels along a channel. So this function U only describes the profile of the wave along the channel. For this reason, U only depends on one space variable and time. Yeah, because the wave, in their approximation, they consider the wave to be that the profile of the wave only depends on a coordinate along the channel. So yeah, so it's the shape is more or less homogeneous in orthogonal to the channel, and so it depends only on coordinates along. Yeah, this was a simple simplification, of course, and then derived by physical considerations. They derived this differential equation. And now this is very interesting, that first by numerical experiments and later by mathematical theory, it was shown that this PDE has exactly the properties which made Lord Scott Russell so excited. Yeah, they have many preserved quantities, and this leads then to this hidden relation between integrable systems and Riemann surfaces. I cannot explain this here, but a major step towards this discovery was an observation of Peter Lex. For this reason now they are called Lex operators. And the observation was that this equation here can be written in this form here. Now that this operator, it's Schrödinger operator, one-dimensional Schrödinger operator, depends on time by a commutator. Okay, and I will not go into more detail. Yeah, and so this finally lead to a completely new description of these integrable systems, and one understands now that more or less all integrable systems, all the integrable systems which were known before, yeah, that they also fit in this scheme. So they also have some relation to Riemann surfaces. Okay, this is the section 2.2. Now let's recall what we have done today. Yeah, we first introduced the linear second order PDEs, then we introduced Laplace equation, we introduced the elliptic class, and then on the boundary of the elliptic class we introduced the parabolic equation with the main example of the heat equation, and then we finally introduced another independent class, the hyperbolic PDEs, with the example of the wave equation. Yeah, and then we finally understood that I made some words about my research. Okay, and so these three simplest examples of this second order linear PDEs, which now came out of this classification, namely Laplace equation, heat equation, and wave equation, this we then treat in the following 3 chapters. Thank you.